Our fourth family of reactions is similar to our third family, except that instead of just one exchange happening from one reactant to another, we now have sort of two exchanges, if you will, and thus the name double displacement for these reactions. Now, the great news about double displacement is that there's really only one scenario to consider, and it's a very simple one. And what we can do is we can use the analogy of being in a traditional square dance. And at a traditional square dance, you would have a gentleman and a woman dancing together, another gentleman, another woman dancing together, and those can be represented by the two couples on the left. And when the person who's announcing the dance says, you know, change your partner, there becomes an automatic change again, maintaining sort of that gender connection of male-female. And so the only way that they can actually change partners is if the gentleman here becomes a partner with the lady over here, and if the gentleman here becomes a partner with the lady over here. And you'll notice that I've written them in an order such the gentleman, which is the metal, is always listed first, followed by the lady, which is the non-metal. So this outside pairing can be written just as is, with yellow first followed by red, which you see here. But when it comes to pairing up the two that are on the inside, we have to make sure that we write this one first, followed by this one, to maintain that metal, non-metal consistency that we have with ionic compounds. So it's just a swap of cations and anions. There are two ionic compounds on the left, and there are two ionic compounds on the right, which makes it very easily identifiable. We're going to look at a couple of scenarios, though. There we go. A couple of scenarios, though, that can result because of these cation and anion exchanges. So the four scenarios are as follows. The first one, we could have water being produced as something on the right-hand side. And if that's the case, it's called a neutralization reaction. And we will get to these a little bit later in the course. In very, very rare scenarios, a gas can be produced. So I'll show you an example of it, but really we're not going to focus our energies on those first two scenarios for now. Instead, we're going to focus our energies on the two that have the double asterisks beside them. We're going to look at when the scenario occurs where these two ionic compounds make a funky chunky or precipitate, or where we mix them together and we see absolutely positively nothing happen. And we'll see if there are some ways to predict whether scenario C or D comes about. So let's go first, though, to A and B, the two that I just want to mention in passing where water is produced. Now, this only occurs when we have an acid and a base react with one another. So the acid that I've chosen is sulfuric acid, or hydrogen sulfate is another proper name for it here, and its chemical formula is H2SO4. Sodium hydroxide is a base because it contains OH ions. By definition, that's what bases are. And so if we do sort of this repairing of outsides and insides, what I'm going to do is I'm going to clone what's on the outside. Now you'll notice I didn't take the two with me because when I repair these up, I'm only interested in making, we'll make the charges match as they come paired. Or become paired. The reason there was a 2 here before is because it was paired up with sulfate, which was a charge of 2 minus, but it's not going to be paired with sulfate anymore. And then similarly, I'm going to clone this one, and these two will come together. I'll put them up here as our first product. Now, HOH is also known as water. So here is our neutralization product of water from an acid with a base. And the other pairing of ions would be this inside one right here, which is the sodium, and we'll take it over there, and it gets paired up with sulfate. And we'll grab just sulfate, here we go, and this is a new partnership. Now, this new partnership, though, doesn't have a charge balance. They're not exactly the same as a 1 plus and a 2 minus. So in their new partnership, they have to be neutral. And so what we will have to do is we will have to take two sodiums or have two sodiums come together in order for them to become neutral with sulfate. We'll have to go back and balance the equation after this as well. So we see we can kind of balance it by cation and anion, which is nice. So our cation, H plus, here on the left, has 2 of them, but on the right-hand side, it only has 1. So we can put a 2 in front of the water. Now what that does is it now creates 2 hydroxides, anions, but if we look at the hydroxide anion on the left, there's only 1 of them, so we can clone it and create 2. Now that in turn, of course, creates two sodiums, but we notice on the right-hand side, we needed two sodiums in order to balance with sulfate, so that's fine. And then finally, our last ion to balance is sulfates, and there's one on each side. So we know now that this is perfectly balanced. Let's look at the scenario where a gas is produced, and I'll do this one very quickly because, again, this is one that is not super common. But again, if we use this notion of let's take the outsides and pair them up. So we'll clone that one, and we'll clone that one. There they are. We're going to take them and have them meet each other as our first product, H plus and S2 minus. Of course, the new partnership is not balanced, so we will have to have two of those. Now this is in fact a gas. This is hydrogen sulfide. It is the smell of rotten eggs. It is not very pleasant. Okay. And if we partner up the remaining two ions, we can take the positive one from here. Again, notice I did not take the 2. I just took the cation itself, which is sodium. There was 2 there before because it was paired up with sulfide, but it is no longer. And we'll take chloride from here, and we'll put these two together to make our other product of the reaction, which is sodium chloride. And they're in a 1-to-1 ratio, which is lovely. If we now go through and balance the equation by positive and negative ions, we can see that the first positive ion is H plus. There's one of them here, but 2 of them on the right-hand side, so we're going to need to clone the left-hand side here. That's going to create 2 chlorides. If we go to the right side, we only have 1, so we'll need to clone the sodium chlorides as well. That creates 2 sodiums, but that's okay because on the left-hand side we had 2 sodiums. And the only other ion that's remaining to balance is the sulfide ion. There's one of them here, and there's one of them here. So now we know that the equation is in fact balanced. And balancing by cation and anion is really cool with double displacement because it doesn't take as long at all as some of the other types of families of reactions. All right, now this is where we get into the meat of things, looking at whether funky chunkies occur. Now the interesting thing we have to do first is all of these ionic compounds that we're reacting with each other, remember, are solids at room temperature. So how exciting would it be to put, solid A into a container, pour it in, could be a white solid, a crystalline solid, and pour in another, say, white crystalline solid, and, stir them up a little bit and wait and wait and wait and wait. Those crystal particles do not have a lot of kinetic energy. They do not have a lot of motion. Therefore, collisions between reactant particles are going to be far and few between, and this reaction is going to take forever. So what you'll notice in this chemical equation is that we've changed the state of matter of our reactants to being aqueous. What does that mean? It means that we have dissolved them in water first. So we've taken a beaker, some water, and we've dumped our little crystalline friends in, and they have dissolved. And this is great because now there are positives and negatives floating around throughout that water. They're moving. The chances of them finding collisions with the other cations and anions that we have from the other reactant are really great, and then we can see the reaction happen much, much faster. So in these double displacement reactions, it's very important to note that we always make them aqueous first. All right. Let's see if we can predict what the products would be using the same set of steps we have with the other two examples. Let's do some cloning. So I've got potassium here, and it's going to partner up with the negative one here. Now note, again, I'm not taking both nitrates over. I'm just going to take the fact that the negative is nitrate. There were 2 because it was paired up with lead before, but it's got a new partner now. It's got a potassium partner. And the great thing about that, of course, is that they have the exact same charge. A 1 plus a 1 minus means, hey, no further balancing in that chemical formula needed. Let's do the remaining pairing. So what do we have left? Well, we have the lead, and we're going to partner it up with the iodide over here. Now, in their new partnership, they are not 1-to-1, and so in order to balance charge, we are going to need 2 of these iodides. Now, when we get to these 2 final products here, we have to ask ourselves, would we see anything fun happen? Would we see any funky chunkies occur, or is this going to be just like watching paint dry and there's going to be absolutely nothing happen? Well, the good news is there's a way to predict this. And I'm going to tell you right now which one's which, and in the next slide I'll show you how you would know. When you mix these two together, this one stays dissolved. It remains aqueous. But this one is super cool. It is like a bright egg yellow when you mix the two of them together. And when you let it sit overnight in a test tube, say, where the reaction occurred, you would see at the very end or the very next day, down in the very bottom of the test tube, all these yellow particles would have settled to the bottom because of gravity, and this would be a clear, colorless solution, and this would be a whole bunch of yellow stuff. It's very, very cool. It's solid. So next slide, how do we know? Well, we have a tool that you've been using all along in this course that has all kinds of little cheats and things for you to make life easier for you in chemistry. And the answer is we can use our friend, the alkane periodic table. And we're going to use something on it called the solubility rules or the solubility table. And it's on the ions side of the table, not the element side. So where is that? Well, if you take out your alkane periodic table of ions, you will find it at the very, very bottom underneath the lanthanides and the actinides. There's a table down there, and what we need to do is we need to learn how to use it to figure out whether what we create is a funky chunky or not. So let's use this example to show you how it works. Magnesium nitrate combines with magnesium sulfate to produce what? Well, from a word equation, this is pretty easy because the positive of this is going to combine with the negative of that, and the positive of this is going to combine with the negative of that. So we get potassium sulfate and magnesium nitrate. Now, from here, you could either go ahead and do the cloning process we've done before, or you could just take those words and put them into chemical formulas, right? Because you can do that. So potassium is a 1 plus, a sulfate is SO4 2 minus, so we would need 2 potassiums to balance that. And then magnesium is a 2 plus ion. Combine it with nitrate, a 1 minus ion. Well, you're going to need 2 of those because, again, charges have to balance. So here's what we have to do next. We have to use the solubility table at the bottom to figure out what is the state of matter of each of these. In other words, do they dissolve well or do they not? So here's what we do. We scan across the top row here of the table until we find sulfate. Now sulfate is a little bit past half. It's right about here. Okay? And then there are 2 rows underneath that. The first row says soluble, and the one underneath of it says low solubility. What we have to do, excuse me, is figure out where is potassium in that column. Okay? Is it located here or is it located here? So in the first row, you will see that it says most sulfates. So I mean, most sulfates are soluble. Most of them dissolve very, very well in water, but there are a few that don't. And the exceptions listed are silver, lead, 2 plus, calcium, barium, and strontium. So fortunately, magnesium is not located as one of those exceptions, so it must be right here, which means it's soluble. And soluble means aqueous. So up here, we can put AQ. It would stay dissolved in water quite nicely. Now let's do the same sort of analysis for nitrate, or magnesium nitrate. Let's scan across the top row and see where we find nitrate, or the negative ion. And you'll find that the nitrates are not very far in. They're just before the halfway mark of that table. And right underneath there, you will see the word all. All nitrates are, in fact, soluble. All of them will dissolve in water really, really easily. And so that means we can put AQ up here as the state of matter for magnesium nitrate. So in reality, if we carried out this reaction, we wouldn't see a whole heck of a lot happen. Not much would. If either one of those had a cation that was in this row down here, then we would say that they're in the solid state. They would form funky chunkies because they have a very low solubility in water. They do not dissolve well. So in summary, double displacement reactions are again easy to identify because you have two aqueous ionic compounds as reactants always. Dissolve them first. And then one of them is always going to be aqueous and the other one is either going to be a gas or water or a precipitate or stay aqueous itself.